Thank you for the introduction. I'm Kunqian from Tsinghua University, and I will be presenting our work, Widar2.0 passive human tracking with a single Wi-Fi link. It's collaborated with Chen Shuwu, Yi Zhang, Guidong Zhang, Professor Zheng Yang, and Professor Yunhao Liu. Location is a key information for context-aware computing. Comparing with active localization, which essentially tracks the devices carried by the persons, passive localization is more convenient and has wider applications such as smart home, health monitoring, and intruder detection, where the persons, the targets cannot or do not want to wear any devices. Two types of instruments are mainly used in passive tracking, RF radios and cameras. While RF devices have less sensing ability, they still have several key advantages, including less privacy concern, larger surveillance area, and more ubiquitous deployment. RF-based tracking thrives with preview RF devices, including millimeter wave, FMCW radar, RFID, and Wi-Fi. As Wi-Fi is the most widely deployed, our work focuses on passive tracking with commercial Wi-Fi devices. Our early effort has demonstrated the capability of passive tracking with commercial Wi-Fi. We proposed Widar. Specifically, Widar measures the Doppler frequency shift, shorted as DFS, caused by person movement. It models the relation between the person's location, velocity, and the DFS, and pinpoint the person passively. However, Widar has several drawbacks. And first of all, the most important one is that Widar requires DFS from multiple links to compute velocity. And second, since CSI contains various phase noises, Widar can only use CSI amplitude to calculate the absolute value of DFS. So it requires trials and error to resolve sign ambiguity. Last but not the least, with only DFS, Widar requires costly search to spot the initial location. Besides Widar, there are also plenty of Wi-Fi-based passive tracking works. However, they either require specialized hardware, which are less ubiquitous, or they require multiple links, which are less practical, just like Widar. So the question we face is that can we achieve both ubiquity and practicality for passive tracking? And a straightforward answer is to use a single commercial Wi-Fi link, but how? Let's suppose a person walks around the link. Some signal is reflected by the person. Now, if we can obtain the time of flight, TOF, and the angle of arrival, AOA, of the reflection in addition to DFS, we can uniquely pinpoint the person by the ellipse determined by the TOF and the ray determined by the AOA. This is a basic idea of Widar2, which tracks the person with TOF, AOA, and DFS of a single Wi-Fi link. The framework shows how Widar2 localizes the person with CSI. As CSI is measured and input, Widar2 first calibrates CSI to remove random phase noises. Then it estimates multi-pass parameters, including TOF, AOA, DFS, and attenuation of each pass. Next, it matches parameters from successive CSI data segments, and the output are parameter series. Among them, DFS and TOF are merged to calculate fine-grained range, which is further combined with AOA for final location. Through the whole process, there are three challenges. First, how to jointly estimate multi-pass parameters in CSI. And second, how to automatically calibrate CSI phase noises. And third, how to derive locations from unmatched and low resolution parameters. Solving all three challenges is the main contribution of our work. Let's first see the challenge of parameter estimation. Due to multipass effects, CSI can be modeled as the multipass responses. Here, PL is the signal of the else pass whose attenuation and propagation delay are alpha L and tau L. In practice, we use indices ijk to refer to the S packet in time, the J is subcarrier in frequency, and the K is antenna in space. Then the delay can be is a combination of parameters TOF, tau L, DFS, FDL, and AOA phi L. Specifically, the left figure shows 4 subcarriers whose phase changes with TOF. And the relative phase between the J subcarrier and the 0 subcarrier is delta G tau L, where delta G is the frequency difference. And the middle figure shows 6 packets received sequentially, and the right curve is a carrier signal. The relative phase between the S packet and the 0 packet is FDL delta Ti, where delta Ti is the time difference between packets. And the right figure shows a signal arrives at an array with 3 elements. The relative phase between the K's element and the 0's element is delta Sk phi divided by lambda, where delta Sk is the location difference and the lambda is the wavelength. Given that CSI can be modeled as multipath responses and each path can be modeled as a function of these parameters, we can formulate the problem as a minimum likelihood estimation problem. Here, H is a measured CSI, and the sum of PL is a computed one given parameters. L is the number of multipaths, and in practice, there's a trade-off in setting L. On one hand, L should be larger than the number of principal multipaths to make estimation more accurate. On the other hand, L should be as small as possible to reduce computation cost. In practice, we set L as 5. And the data input is CSI segment, which consists of CSI from all 3 antennas, 30 subcarriers, and packets received within 0.1 second, during which the parameters are assumed not to change significantly. We use Sage algorithm to estimate parameters. It is a general version of expectation maximization algorithm. Comparing with the standard one, which requires simultaneous updates of all parameters, Sage allows updates of subsets of parameters in turn, which reduce the dimension of searching space and is more efficient. And specifically in the E step, Sage decomposes CSI and calculates each multipath signals with the parameters estimated in the last iteration. And in the M step, Sage searches for the optimal parameters with minimal error using the multipath signal calculated in the E step. For the second challenge, as we know, CSI contains not only channel response but also various unknown phase noises. Here, epsilon Ti and epsilon F are the timing alignment offsets and carrier frequency offset. Existing active localization approaches use linear regression to estimate and remove the phase noises. However, it is infeasible to passive localization. And the main reason is the reflection from human bodies orders of magnitude weaker than the static signal, such as the line of sight signal or the signal reflected from surrounding walls. So the residual after calibration is still comparable with the reflection and may cause obfuscation. The left figure shows an example of the Doppler frequency profile when a person first moves away from the link and then towards the link. And as shown in the right figure, the phase cannot be correctly recovered by after calibration. Our solution is based on observations that these phase noises only change in time and frequency, but not in space. So we select an antenna as reference and compute the conjugate multiplication between each antenna and the chosen reference. We further classify multipaths into static signals with zero DFS and dynamic signals with non-zero DFS. And we then prove in the paper that the product can be approximated as the sum of target term, which is the product of the dynamic signal and the conjugate of the static signal. The target term has the same phase structure as the original dynamic signal. Specifically, the TOF is tau L minus tau N, where tau L is the TOF of the dynamic signal and tau N is the TOF of the static signal. It is a line of sight TOF and can be measured in advance since the devices during tracking is fixed. In addition, the AOA and DFS of the target term is the same as the original dynamic music. The original dynamic signal. So the product can has the same phase structure as the original CSI and can be used in stage algorithm. For the third challenge, as multipass parameters estimated are cluttered together, it is not straightforward to select parameters of reflection. And this figure shows an example of the output of parameter estimation. And as you can see, there are AOA of the residual line-of-sight signal and the DFS of the mirror term and spreading noises. To overcome the interference, we propose a graph-based path matching algorithm. And specifically, we build an n-partet graph. And the vertices in the s-partet is the multipass parameters estimated from the s-CSI data segment. And the weight is the distance between multipass parameters. Our goal is to search for an optimal assignment with minimal overall weight. So instead of searching for the local optimal assignment between adjacent partets, as you see the solid line in the figure using some algorithms like Hungarian algorithm, we search for the global optimal assignment, which forms an n-order complete graph. As you can see in the figure, it includes the solid line and the dotted line. And as shown in the figure above, you can see the global optimal assignment is more robust to noises in comparison with the local optimal assignment. And finally, we refine range for localization. Now we have TOF and DFIs. However, simply using any of them to calculate range is insufficient. On one hand, TOF can provide absolute range. However, it suffers from noises and low resolution. On the other hand, DFS can only provide the relative change of range. So instead, we merge TOF and DFS with the Kalman smoother and to calculate the fine-grained range. Now with range and AOA, we can directly pinpoint a person in the monitoring area. To evaluate Widar2, we use two laptops with Intel 5300 cards. Both one is a transmitter and the other is a receiver, and both works in monitor mode in channel 165, and the packet rate is 1000 Hertz. And here are three scenarios we test: the classroom, corridor, and office. And the figure below is several tracking samples in the scenarios. And due to time limitation, I will only introduce the overall performance, and I will show the other experiment results in discussion if you have interest. And the left figure shows the overall localization accuracy, and Widar2 achieves median tracking errors of 0.75 meters and 0.63 meters with 1 and 2 links respectively. In the 2 link case, we calculate the weighted sum of locations from 2 links. The weight is proportional to DFS, since larger DFS leads to clearer extraction of reflection. In practice, by orthogonally deploying 2 links, we can make sure at least 1 link can observe significant DFS. Then we compare Widar2 with 2 state-of-the-art, the dynamic music, which uses AOAs of 2 links to localize the person, and the Intel track, which uses DFS of the 2 links. At first, calculate velocity with DFS and then integrate velocity for location. As shown in the figure, Widar2 outperforms dynamic music, since the latter one uses only AOA and cannot compensate localization error with motion continuity indicated by DFS. On the other hand, while the average performance of Widar2 is slightly worse than indoor track, The latter one has a longer error tail since it calculates the location by integration and suffers from error accumulation. In contrast, Widar2 uses absolute time of flight, so it's free from the effect. It's also worth it to note to show the impact of sampling rate. Here we start with 1,000 packets per second and gradually discard CSI collections to simulate a packet rate of 500 Hertz and 250 Hertz. As shown in the figure, Widar works moderately even with 250 packets per second. And it is also noted that the minimum rate is 200 packets per second for uniqueness estimate of DFIs. We further evaluate the computation costs of Widar2. And as shown in the figure, the main computation cost comes from the iterative optimization in parameter estimation. Given that Widar2 can work in a packet rate of 250 packets per second, the corresponding per second processing time, is 0.7 seconds. So it enables real-time tracking with Widar2. So in conclusion, in this paper, we propose Widar2, a practical passive tracking approach with a single Wi-Fi link. And we implement it on commercial Wi-Fi devices, and it enables achieves dynamic decimeter level tracking accuracy. That's all. Thanks for listening.
Okay, let's thank our speakers.